Hi, good morning. First, I want to thank David, I want to thank Greg, I want to thank Wang for putting this together. I'm pretty excited about this. I like this set of topics. I think it's really interesting to have approximation theory perspective on machine learning and probably vice versa too. It is my tradition to take a photo of the audience before we start, okay? So I'm going to put it in pano mode. Give me just a second to figure out how this thing works. Amr, if you want to, like, after I finish here, if you run behind me, you'll get in both sides of it, which is really cool. You'd be surprised how many people actually take me up on that. 0. Maybe you wouldn't be surprised. Smile. And get all the way over to David. All right, now we have a conference photo, too. If you want to find this photo, you can find it on the internet. You can follow me on Twitter. I am at Dr. Polynomial. Wow, that's a good response for a Saturday morning. I appreciate that. Thanks. As David said, I'm Paul Constantine, assistant professor in Department of Computer Science at CU Boulder. I'm going to be talking about approximation theoretic advice for supervised learning. That sounds pompous, and I don't mean it to be. I mean it to be personal. So this is a very personal talk for me, sort of like my perspective, coming at this material from a number of different sides. My undergrad's in math. I was in a math and stats department. I did a postdoc in mechanical engineering. Now I'm in computer science, so I've been across all the disciplines. My degree says computational and mathematical engineering, so it's like all of the words except statistics. So to get a feel for the audience, how many of you identify as mathematician? All right, lots of mathematicians. How many of you identify as statistician? A few statisticians out there. How many of you identify as computer science? Oh, you identify as both. Okay, there's both. How about engineering? Oh, yeah, look at this. Cool. All right, so notice that we've got a broad range of perspectives here. So this is going to be, I'm trying to make it somewhat perspective agnostic. Of course, that's never possible. And so I'm going to try to cover a couple different perspectives in a short amount of time. And of course, the trouble with that always is that you run the risk of making everybody mad. So if you're mad at me after this talk, good. It means you were listening. And you can come talk to me in the coffee break. Cool? OK. So with that, I want to start with my favorite quote from John Tukey from his famous book, Exploratory Data Analysis. He says, "Even more understanding is lost." By the way, I'm quoting his font choice here. Even more understanding is lost if we consider each thing we can do to data only in terms of some set of very restrictive assumptions under which that thing is best possible. Assumptions we know we cannot check in practice. And I really, really like this quote. And the way that I think about this quote in the practice of machine learning is don't trust theoretical guarantees in your algorithm if you can't verify that your problem or data set satisfies the assumptions needed to derive those guarantees. Right? That's sort of how I interpret this in the context of machine learning now. And so what I'm going to be talking about, regression and approximation, and talking about the problem setup for each of these. This is a colloquium talk. It's meant to be somewhat introductory. So I'll be talking about the problem setup to talk about the story of where these problems come from mathematically, and about whether or not we can trust things like error estimates coming out of the methods. So this is actually the first part of my last slide, and I'm going to give it to you now because you all have your coffee in front of you and you're somewhat awake and paying attention. And so my first bit of practical advice to everyone is civilized conversation and argumentation. Okay? We have a tendency, all of us in academia have a tendency to be a bit reductionist in the following sense. If you're from computer science, or let's say you're from statistics, something I'm somewhat more familiar with, and then you see a method in computer science, there's this tendency to say, oh, that method is just this other thing. Right? And there's this word just, right? It's like, oh, that's just this, or that's just that. I would encourage you to to fight that initial response of reductionism to say, oh, that method that I saw is just this other thing. Instead, say, think about it as an opportunity, right? Like, oh, this actually looks kind of similar or related or an analogy to the thing that I do, and it looks like there's some connection there. And that's something that we ought to explore at the coffee break, okay? Yeah, and also don't be afraid to say, I don't understand, right? None of us in here are experts in all of the things. And so someone in here has expertise that you don't have. Don't be afraid to say, wow, I don't really understand that perspective. Can you tell me more about it? So I wanted to start this conference on approximation and machine learning, approximation theory and machine learning, arguably different perspectives coming at arguably the same problem or same sets of problems. On this tone of collegiality, of civilized conversation and argumentation. Okay, be nice to each other, give everybody the benefit of the doubt, drink beer, go on a hike, talk about the math. Okay? Cool. All right. Yes?
That is just a categorical imperative by cat.
by cat? Yeah.
Sorry.
That's okay. I also want to put up trigger warning. So one of the things about interdisciplinary conversation is that we use similar words, and they often mean different things, or at least come from different contexts. And the contexts are very important. So I'm going to be using words like data, model, noise, parameter, error, uncertainty. I'm actually not going to talk about overfitting, but overfit is one of those words too, where I know that statisticians have some very precise meanings and definitions for some of these words like noise, like parameter. And often mathematicians use these words a little bit more loosely depending on the context. As long as you define it, as long as you're consistent, everybody's fine with however you use your words. But I can tell you a story from the uncertainty quantification uncertainty quantification conference where an esteemed speaker was giving a plenary talk, and my statistician colleague is texting me and said, well, I can't listen to someone who doesn't know the difference between parameters and variables, right? And I'm going, okay, well, they're using them consistently. So anyway, all right. So like I said, this is my trigger warning. And again, beware when you have conversations at things like the coffee break for words like this, to make sure that before you just run with this, assuming you have the same idea of what data is, talk about it, right? Oh, that's your data? I think of data a little bit differently. Here's the data from my context. What's the data from your context, et cetera. Yeah.
Mathematical safe space we can go to?
Oh, I like that. Mathematical safe space. We should have that. That's a great idea. Okay, like I said, this is a very personal talk for me, so I want to give you a little bit of the background of the literature that sort of brought me into this set of ideas. So I sort of started in the uncertainty quantification world as a PhD student, and which is arguably where a lot of approximation theory is happening now in the practice of engineering. And so books like the book by Ghanem and Spanos, the paper by Dongbin Xu and George Karniadakis on polynomial chaos. People like Fabio Nobile, Raul Tempone, and Clayton Webster and their work in sparse grids. And then I sort of went through this and I was like, oh, it turns out this is polynomial approximation. And so Walter Gauci's book on orthogonal polynomials just like changed my worldview when it came to approximation theory. So again, this is I'm just sort of trying to give you a sense of like the literature background that I'm coming from. When I got into my postdoc, I started looking more into the statistics literature. And so I found Art Owen and Jim Kohler's paper on computer experiments. It's like a whole other world that's arguably trying to do the same kind of problems. And then I found Don Jones's paper, a taxonomy of global optimization methods based on response surfaces. And all of this response surfaces was like, oh my gosh, you can combine polynomials and radial basis functions? Wow, and everybody knew that like way a long time ago? Cool. And now, more recently, I've sort of been getting more into the stats literature. Here's the regression graphics book by Dennis Cook. Again, just giving you a sense of sort of where I've been coming from with this material. If you're familiar with this material, then you sort of have some idea of where I'm coming from. Okay, I'm going to begin by contrasting regression with approximation. Okay, so this book here by Weisberg, Applied Linear Regression, this was the textbook for the grad linear models class at Stanford that I actually took for 1 week and then I dropped because I had to take another class. But I got the book and the book's cool, and then as part of my thesis I did a lot with this book, Introduction to the Approximation of Functions by Rivlin. Okay, I have a couple notes here that I want to emphasize. Again, I want to emphasize this is my perspective, sort of coming at this material from the background of this literature. This is meant to start a conversation and not be the final word. I suspect that all of us in here have our own perspectives on this material. So I'm trying to make it as simple as possible to make the contrast as stark as possible. So I'm only going to be working in univariate approximation. I'm not doing anything multivariate. Some of you know I love working in high dimensional problems and working on dimension reduction. I'm not going to talk about any of that today. Both of these are semester-long courses, and I'm going to talk about them both in the span of about 30 minutes. And so, again, the danger in such an attempt is missing both of them, making everybody mad. And then, of course, if anybody likes this and wants to write a review paper, then let's talk at the coffee break. Okay. Regression and approximation looks like they start with the same thing, but these data sets come from very different backgrounds, have very different stories associated with them, so let's walk through those. Let's start with regression. Regression assumes that you begin with these pairs, these input-output pairs, or a statistician would call them predictor-response pairs, and they are independent, identically distributed samples from some unknown joint density on the combined predictor-response space. Okay? Once you're given these pairs, then the goal is to statistically characterize this random variable. Y given x is a random variable, and we can statistically characterize it by, for example, computing moments of this thing. Compute this is the regression surface, and this might be the variance of the regression here. So now this is the problem. Notice where the data comes from, and notice what our goal is. How are we going to accomplish that goal? We'll start by building a model. We'll build a model for y as a function of x. Here, this is some function that represents our model for the expected value of y given x that depends on some parameters theta. This thing over here is a modeled random variable. It's zero mean, independent of x, and is meant to model sort of the noise in the data. That's one way to interpret what this epsilon is doing over here. Once we form our model, this is our model for representing y as a function of x, then we can do a fit, something like maximum likelihood, where we can get the best theta relative to some kind of loss function or cost function. This is just a mean squared cost function. And now we can predict. So now I build some kind of I find my theta, I plug my theta into my model, and now I can evaluate that model at any of the x's to get an approximation or some model for the expectation of y given x at some other x's. Statisticians get really excited because then they'll call quantifying uncertainty evaluating what sort of the prediction range of this prediction is. Okay, so if you're a frequentist, this is a confidence interval. If you're Bayesian, this is a credible interval. Okay, but what I want to note is the story where this curve and where these lines come from. On the approximation side, I'll give you a little bit sort of the background. Oh, my name tag's fallen off. You guys can read this, right? Okay. So on the approximation side, we typically start with some kind of very large class of functions, something like the class of continuous functions. And then within that, there's some smaller class of functions, say polynomials of some fixed degree n. Now, the questions that we ask in approximation theory are the following. For some function from this big class of functions, where is the best approximation in my smaller class of functions to that given function? And is that best approximation unique? Right? This is a mathematical question. Right? In math, we ask I tell my students constantly, when you are presented with a new problem, what is the first thing you ask? Does the problem have a solution? Right? So does the solution exist, and is there a unique one? And that's the kind of thing we ask in approximation theory. Assuming that we can answer that question, then we might ask, how does that best approximation behave as a function of some parameter of this approximation class? Right? So if I increase the degree of the polynomial, how does my best approximation behave as that parameter of the polynomial degree increases? Now, since I want to do things on a computer, what I really want is an algorithm. So if you give me some f, then how do I compute that best approximation? Okay? Or something close to that best approximation. And usually what we try to do to analyze the error of this algorithm is to say that for the thing that I can actually compute, I try to make some relationship with that best approximation error, such as it's bounded by some constant times, bounded above by some constant times that best approximation error. Okay? Notice, this is a really different story than regression. Really, really different story. So where do those dots come in, the dots on the line? So within approximation, our starting point is some function. We are given a function. We're not given data from an unknown density. We're given a function, and then possibly a known density on the inputs or the domain of that function. And now our goal is to find some kind of approximation of that function such that this error is small. And the way we'll do that is do some kind of constructive algorithm. So the constructive algorithm will start by saying, let me first choose some points x. Let me evaluate my function, which now gives me sort of the input data to my algorithm for approximation. And now I'll fit some kind of a curve that goes through this data, say, for example, by least squares. Right? Just basic least squares polynomial fitting. All right, this picture looks really similar to the last one we saw from regression, right? So these look identical if you just look at them. But the story of the data and the fitted curve is different, right? In both of these cases, where did this data come from, and how do you interpret this curve? How did you create this curve? Where did it come from? And the question is, does it matter? And I'm going to argue, yes, it matters a lot. Okay? Why does it matter? Well, it matters, for example, if we want to talk about error. So what does error mean in the context of approximation or regression? All right, let's start with regression. So if this is the story of where that data came from, then a regression analyst is going to compute something like a confidence interval, right? You might use a plug-in estimate of the standard error, and notice so for some point where you want to predict, and notice the relationship between this error bar. It's not an error bar; it's a confidence interval. And that underlying density that you believe generated that data. In contrast, the approximation error is well defined, it exists, and it's just the absolute value of the difference between your fitted curve or your approximation and the true value of that function. And of course, this might be some kind of pointwise error. We usually roll that up into some kind of a norm, maybe a root mean squared norm, or an L2 norm, or an L infinity norm, or a sup norm, something like that. Here's one part that gets really tricky from the point of view of the algorithms. This is computable from the data. Just from the given pairs xi and yi, you can estimate this thing. You can use this plug-in estimate of the standard error. This one is not without computing the function again. Right? So I think that's really interesting, and I think that in my experience as an engineer, this has caused some confusion where people will compute this and assume that it is this. And I think I hope that it's really clear from these pictures that this thing is not this thing. Right? And we're going to get to the point, I'm going to move from this to Gaussian process regression and radial basis function approximation, and then it's going to get even more complicated. But we have to start here. Right? We have to start with the difference between just regular least squares approximation and regression. I like to tell my students that least squares is a subproblem of regression. But the regression problem includes this entire story about where this data came from. And that entire story is what allows us to compute to interpret this error bar, right? Or confidence interval. Again, I'm being a little bit loose with the terminology, in part because I'm going back and forth across disciplines. But the story of where the data came from is what allows us to compute this. There's another place where this contrast is very stark, and it is convergence. So what does convergence mean across regression and approximation? Again, here's the story of where the data came from. From a frequentist perspective of the regression, as the data increases, we get root n consistency in our parameters. Okay, so the theta hat, which is a random estimate of the true parameters theta, which gives you a random estimate of your approximation of the conditional mean, and these things converge as the data increases, and they converge at a rate of 1 over root n, where n's the size of the data. Okay. If we increase the data and we recompute things, then we get a slightly different estimate. But ideally, this thing ought to converge as I draw infinitely many samples from this joint density. In contrast, when we talk about approximation theory, as the approximation class grows, meaning you can think of as our degree of polynomial increases, we want this error to go to 0. Right? So I start here with an initial set of points, I fit some curve, but then maybe I'll draw more points in order to enrich my approximation class. Or the other way to think of it is, I want to enrich my approximation class, and therefore my constructive algorithm requires more points. So I'll draw more points, and I'll fit another curve. The convergence rate for this kind of approximation, it depends on the function that you're approximating. Broadly speaking, it usually depends on something like smoothness. Smoothness is measured in many different ways in mathematics. It could be measured by higher order derivatives. It could be measured by the size of the region of analyticity of the function. Or it could be measured by something like the Chebyshev coefficients, and these two are intimately related too. But again, these are some measures of smoothness. If you really want to distinguish, like just at a coffee break level, the difference between sort of regression and approximation, ask the person that you're talking to what happens as the polynomial degree increases. Is that better, or does that lead to overfitting? Right? Because a regression analyst doesn't want the polynomial degree to increase to infinity. That doesn't make any sense, because then you're fitting noise as opposed to fitting the function. But that idea doesn't make sense in the approximation sense. In the approximation sense, we will readily take our polynomial degree to infinity, because that's how we get our asymptotic error estimates. That's how we measure how good our constructive approximation algorithm is. But if you tell a regression analyst, yeah, I've got one predictor, one response, and I'm doing a polynomial model of degree 65,000, they're like, what? That's ridiculous. However, if you go look at the ChebFun approximation software from Nick Trefethen in Oxford, their highest degree of Chebyshev polynomial approximation for univariate functions is about 65,000. Right? And they will go all the way there if they have to get to the point of being sufficiently accurate for their functions. So I think this is a really useful contrast to kind of distill the differences between regression and approximation. All right, so now let me move on to this contrast. So how many of you are familiar with Rasmussen's book on Gaussian processes? A number of people. How many of you are more familiar with Wendland's book on scattered data approximation? A couple people? Okay, or some of you are just not very bold this morning. That's fine. So now my goal is to do a similar type of contrast between the Gaussian processes for machine learning and scattered data approximation coming out of the radial basis function kind of approximation community. Okay, so we'll start with similar pictures. All right. Again, on the Gaussian process regression side, I have some dots in a box, and on the radial basis approximation side, I have some dots in a box. So let's go over what we do for Gaussian process regression, or what Gaussian process regression does. We begin with some kind of pairs, xi and yi. Notice there's not that same story here of them coming from some joint density necessarily. What we are going to assume instead is that these yi's are one realization of a Gaussian process. Here is one realization of the Gaussian process that goes through the data. I've denoted it by choosing a particular omega here as the one realization of this Gaussian process. And what I believe is that this data comes from one realization among many possible realizations, all of which go through that data. Okay, so you'll see a lot of plots like this when you talk to people that do computer experiments in Gaussian processes. Given this data, we'll now choose some kind of a correlation model along this axis, meaning if I pick 2 points on this axis, what is the correlation between those 2 points? And that correlation model is typically parameterized with some kind of a theta. It's a little bit weird, though, for me personally. When I first started, it took me a long time to kind of understand what was going on here, because from a frequentist perspective, this is all you're given, right? You're given 5 points. Now, is that 5 samples? No, it's 1 sample. And it's actually one discretized sample of 1 sample. So what if I told you, I tell you that a sample from my random variable is 7. What's the mean of that random variable? That's hard, right? Unless you begin with some kind of like all-encompassing prior around all of the knowledge in all of the world, then it's really difficult to say, okay, I have 1 data point, 7, and now I want to estimate statistics of this distribution, right? But this is what we're trying to do with Gaussian process regression. And so we choose this correlation model. And what's interesting is that this theta can make a really big difference. Okay, so if theta right here is like a correlation length in some kind of an exponential squared correlation model, this is 1 correlation length. If I increase the correlation length, then all of a sudden all of my possible functions that could have generated this data collapse. If I make that correlation length really small, then all of a sudden look at all these possible functions that could have generated this data. So how do I choose from among all of these possible models for where this data came from before I even do some prediction? Right? This is some kind of like model selection problem. And so one way to do that is to maximize some kind of a likelihood function. I'm skipping some details here. I suspect someone else is going to talk about Gaussian processes, and we'll put some of these details up here. Again, I want to sort of give the big overview picture in order to contrast this with radial basis functions. So you've got to find some theta that maximizes some likelihood of some function of theta that statisticians call the likelihood that depends on the given data. After you do that, now once you find that theta, now you can predict. And you can compute the expectation over this random coordinate of that g of x given the data. And that turns out to be you can write this as a linear combination of your y values, of your given y values, with some weights where the weights depend on the x where you want to evaluate this thing. And you do this for a whole bunch of x's, and then you get something that looks like an interpolating surface. I wrote blue here because in kriging, they'll call this the kriging and Gaussian processes are very similar. They'll call this the best linear unbiased estimate. And to me, that was a fantastic sales pitch, right? This best, oh my gosh, it's best and it's unbiased? Oh, cool, that must be really good. But you have to understand this notion of best and unbiased as coming from this particular story of where the data came from. Right? That's what best means. Now, what's really confusing for an approximation theorist is that we use the word best also, but we use it differently. It does not mean, when an approximation theorist says, give me the best approximation, it does not mean best in this sense. It does not mean best as an expectation over some notion of randomness behind the class of functions that might have generated the data. Okay, but this is what you do, and then you can quantify uncertainty. So the people within the computer experiments community, which is a subset of statistics that works on computer models, they will call quantifying uncertainty to be able to compute the variance of this g function for any x given the data. And there's a complicated formula that's based on this kernel. And again, I think we'll probably see this formula come up some other times during this weekend. But what this gives you is something that smells like an error bar. And sometimes they'll use the word error bars, but really this is more like a predicted uncertainty that all depends on this story about where this data came from. Okay. If I fuss with theta again, I can really make these error bars kind of do whatever I want. So that's why I'm really hesitant to call them error bars. So if I make theta bigger, then I can make those confidence intervals or credible intervals much smaller. If I make theta smaller, then all of a sudden they blow up. Okay. So there's one of the big important problems is modeling here. One way that I have seen statisticians and machine learners try to come up with a better model is to solve this problem better. Right? This is potentially a very nasty optimization problem. It's certainly not convex in theta. There are likely many multiple local minima. These can be really, really hard problems to solve. And so to me, that's, yeah.
I have a question, and it might be kind of dumb, but
Please.
for the predict or the blue method,
Yep.
I'm a little confused because I have a particular background and may not be completely aligned with this.
Okay.
I don't think of it the same way. But the theta there, is that random or not random? Or are you taking expectation over it in that expectation under the predict?
This expectation here is over the random coordinate of the model of the Gaussian process that generated the data.
Subject to the constraint that the observations you had were correct.
Yes.
That equation.
Yes.
Then where does the theta play the role?
So the theta comes in as a parameter to this correlation model.
Okay.
Yeah.
Okay, but it's not a parameter of the underlying distribution for the g's there? Is there a theta in the g?
So this correlation model here is intimately related to the Gaussian process model. So this is a correlation model for what happens for a class of functions of x. Yep. Okay, thank you for asking questions. I appreciate that. Anyone else who has questions, yell at me like that. And if you say, I think this is a dumb question, that's totally fine. We all ask dumb questions when we talk cross-disciplinary, right? Okay, so I like to think that interdisciplinary communication is really just a euphemism for working with people. And working with people requires things like human interaction, something that a lot of us don't really like because we like to sit and work on our computers, right? But if what you want to do is talk across various meanings of words, then you have to do human things. And so please, if you think your question's dumb, don't be afraid to ask it, especially in this cross-disciplinary context. All of us are past our undergraduate courses, right, where there really were dumb questions. And we like to tell the students there are no dumb questions. But then we get some question, we're like, oh my gosh. You really thought you should ask that in front of everybody? But here, this is not that setting. Everyone here is perfectly qualified to ask questions about, like, I don't understand what that word means in that context given my background, right? Okay. Yes?
So is the prediction for the same realization?
Say that again?
Is the prediction for the same realization of the process?
Is
for
the
same omega?
Well, so this is in some sense an abstract model, right? So the prediction is the expectation. It is not for a particular omega. It is the average over all the omegas. Yeah. Okay. Let's go to RBFs, radial basis function approximation. Again, the approximation perspective starts with a different story of where this data came from. Radial basis approximation begins just like in the polynomial approximation with some kind of queryable function f of x. And also some set of centers or some set of points along this x-axis. And now the goal is to find some function s of x such that this error is small. And in radial basis approximation, you're also typically looking for an interpolation also, which I didn't put in the slides. But the first step is to query the function at those centers. This now gives you your input data. And again, data is interpreted a little bit differently here. But the input data for some kind of an algorithm. Then we'll choose some kind of a kernel, something like an exponential squared kernel, for example. And you have to choose this parameter, which is related to the length scale of your kernel. Now, some of you are looking at this going, didn't I just see this on the last slide? And yeah, it looks really, really similar, right? The interpretation is different. Once you choose this kernel, this defines a basis for your approximation. So for each of these centers here, I have a function that is centered at the centers, why they're called centers. And now I can do some kind of an approximation using this set of basis to interpolate this data. So I'll compute some kind of a coefficient, some coefficients that typically involves solving a linear system, where the linear system is related to this kernel function that you've chosen, and then you predict. So for some other x's, you evaluate your basis function and take a linear combination of those basis functions with the coefficients, and you get something that interpolates your data like that. Okay, radial basis approximation. Again, these pictures look the same. And in fact, point-wise, the Gaussian process mean conditioned on the data, so the conditional mean of the Gaussian process is the same as the radial basis interpolant with that kernel, where the kernel is the same as the correlation model for your Gaussian process. Those two things are the same. Okay. However, the story of this data and the fitted curve are very different. Right? Again, this fitted curve is coming from this idea that there was this class of functions, and I have some probability model on this class of functions, as opposed to one given function that may have come from a reproducing kernel Hilbert space. But it really is one function that generated this data. I did this at 3 last night, so I didn't have time to go through sort of the same neat set of slides to go through the error. So instead, I just have text. So let me give you a couple comments on the error and the convergence of radial basis approximation compared to Gaussian processes. Gaussian process conditional variance is not error. Okay? It is not error in the sense that an approximation theorist thinks about error. It is this predictive, if you're Bayesian posterior, confidence interval or credible interval on this blue line prediction that comes from this story about the class of functions that are associated with that particular kernel, correlation kernel. RBF error estimates are asymptotic in the fill distance. What's the fill distance? The fill distance is how far apart are these points? Okay, which again is something that we think about a lot in approximation theory. Right? How do you choose these points, and what happens asymptotically as the number of points increases? So to note that they're asymptotic is also interesting. Right? It sort of reveals a limitation behind the approximation theory in practice, because in practice, as Sven will tell you, if you're at the labs, you have a fixed set of data sometimes. Maybe you can run a couple more experiments, but it's hard to get into that asymptotic regime. So it's hard to believe that the RBF error estimates, which are asymptotic in the fill distance, are going to help you sort of like understand what the error is in your approximation. And actually, this situation gets way worse in high dimensions. Both approaches make practically unverifiable assumptions about the origin of the data generating function and process. I remember my very first slide, not past my title slide, that if you can't verify assumptions, then it's hard to trust theoretical guarantees. Okay? So this is true of both of these. As a caricature, statisticians try to reduce the error by finding a better model. For example, solving the fitting problem better. Remember I talked about that really difficult optimization problem to find the parameters of your correlation model. And in fact, on the RBF side, people will often use that fitting procedure as a heuristic for choosing their scale, what they'll call the scale parameter. And as a caricature, a mathematician will try to reduce the error with more queries or to sample into asymptopia. Yeah, David?
You've just poked a pet peeve. Should I yell at you now or in the coffee break?
Let's yell at me in the coffee break, because I've got 15 minutes left and about 10 more minutes of material to go through.
You just say what the pet peeve is?
So the RBF error estimates, yes, there are error estimates that are asymptotic in fill distance. There are also power function based
Yes.
error estimates that are the basis for it. That look a heck of a lot like the types of formulas that you see in the Gaussian process setting.
Yes.
So it's not always the case that you get error bound by assuming uniform fill.
Yes, but it's also difficult to compute those. Right? And in fact, thank you for bringing up that pet peeve, because that brings up a point that, again, this is a personal journey for me. So let me tell you a little bit about my personal journey with this material. As I began to study as I began to, from the approximation perspective, I knew a little bit about RBFs. As I began to study Gaussian processes, they keep computing these conditional variances and say that they're quantifying uncertainty. By the way, a lot of where this radial basis function approximation, shows up in scientific computing is in the context of computing the solutions or estimating the solutions to differential equations on computers, right? Meshless methods, which is a really difficult thing to say 3 times fast. Meshless methods are sort of based on radial basis approximation. And what always confused me was, in stats they do these variances and they call them quantifying uncertainty, but nobody does it in the approximation community. And I was like, why? Why not? And for me, that was a really motivating question for trying to understand these differences. Why don't RBF people use these posterior variances or confidence intervals as some measure of error? And I think it's because they're different. Yeah?
Make a comment about that. What you mentioned, the error estimate here is what we call a priori error
Yes.
estimation.
Yes.
But in the numeric PDs, we do have a field called opposite.
There's also a posterior error estimates.
It
Yeah.
is trying to quantify.
Yes.
Not the static.
Yes, it is trying to quantify it, but it doesn't look like these, right? It doesn't look like that formula that I wrote as literally formula.
No, the purpose is we're not trying to go to asymptotic region.
Right. Yes. Yeah.
Just
Yes.
a comment.
Yeah. No, I appreciate that comment. Thank you. Okay, so that was my story. Now, like I said, I sort of come from the background of uncertainty quantification. In uncertainty quantification, the problems that we deal with look like computer simulations of physics models, right? And oftentimes our computer simulation is really expensive, so we can run a few simulations, and then we want to build some kind of interpolating surface, a response surface, a surrogate model, an emulator. There's all kinds of words for this, okay? This is the background where I come from. And so I think one of the really important questions is, of these stories of where the data come from and their associated algorithms, which one is a computer simulation? Okay, so which one, if your data is derived, let's say your function comes from some computer simulation, which one of these perspectives is most appropriate? The computer experiment sub-community of statistics thinks that Gaussian processes are the end-all be-all for modeling functions that are derived from computer experiments. Within the uncertainty quantification community that sort of came more from applied math and engineering, there's a lot of polynomial and radial basis approximation, right? Again, they're just different. They're different stories where they came from. But so I want to say something about this question about which one is a computer simulation, and I'm going to argue that it's really complicated. Right? That like a good professor, I'll say it depends. Right? So what is, and the answer to this question hinges on what does error mean in a computer simulation? Because once you can figure out what the error means in the computer simulation, then you can put yourself in one of these contexts. So here are some ideas of what the error means in a computer simulation. These are sort of the foundational papers within that field of computer experiments and statistics. Design and analysis of computer experiments by Sachs et al. From '89. Bayesian calibration of computer models by Kennedy and O'Hagan in 2001. I will tell you that, again, from my personal opinion and perspective, I am not particularly persuaded by this perspective of modeling error in a computer simulation. It's just my perspective. Whether you're Bayesian or frequentist, I sort of think that there was a little bit of like, how can we take this approximation problem, phrase it as an inference problem, and then use the tools that we really like? Mathematicians do this a lot. Statisticians also do it. But for me, it hasn't been compelling. There's also some recent work on probabilistic numerics that tries to reinterpret a lot of numerical analysis from kind of a Gaussian process or probabilistic point of view. Okay, coming out of the national labs, like Sandia, they have this paper, Error and Uncertainty in Modeling and Simulation by Oberkampf and a whole bunch of others. Some of these are managers at Sandia. This, if you're from the UQ world, this is where terms like the distinction between epistemic and aleatory uncertainty come in, which also for me has never been really compelling and kind of strange. Here's the one that I like. So going back to 1947, von Neumann and Goldstein wrote numerical inverting of matrices of high order. And by the way, back in 1947, matrices of high order was like 20 or 30, which is pretty funny. But the first chapter of this paper that was in the bulletin, the AMS, talks about the sources of error in a computation. And I want to walk through those really briefly to give you a sense of what I think is a compelling argument and a compelling description of error in a computer simulation. And they begin that chapter with this really nice caveat, a very epistemically humble kind of statement, this is one way to do it. So they say the analysis of the sources of errors should be objective and strict in as much as completeness is concerned, but when it comes to defining, classifying, and separating of the sources, a certain subjectiveness and arbitrariness is unavoidable. With these reservations, the following enumeration and classification of sources of errors seems to be adequate and reasonable. Oh, that's really good academic hedging, right? It's just like hedging your words, it seems to be okay, don't hold me to it, I don't want to be accountable for this. But let me tell you where these sources of error come from their perspective. So they begin with the mathematical model, or arguably or another way to phrase that is, how well does the math model approximate reality? Right? So we have equations, and then we have measurements in a laboratory, and how good are those equations at sort of representing what's happening in the laboratory where we can do measurements? In uncertain quantification, this is often called model form error. They also mention errors in observations and parameters. And in the uncertainty quantification world, we'll sometimes call this forward and inverse UQ. And really, most of the UQ methods literature is kind of obsessed with this particular type of error in a computer simulation. But then there's this other one that's really important that we don't think about very much in UQ, and we need to. And this comes from, again, this is from, I call this the catechism, by the way, and I kind of hope this catches on because I think it's really cool. This comes from, the two other sources of error are what they call finitistic approximations. I don't think that's an English word, but they use it. And really, the way that you deal with finitistic approximations is sort of the asymptotics from classical numerical analysis. So errors like, how do you compute the value of a transcendental function that admits an infinite Taylor series, but on a computer because you don't have infinity? Or you have an iterative method and you have to stop at some number of iterations. This is where the finitistic approximation comes in. And then of course, numerical round-off, or round off in your floating point accuracy, floating point precision. Again, which is a very common subject for numerical analysis. And you might call this deterministic numerical noise. Von Neumann actually proposes that you should model this with a random variable, but that was 1947. I kind of feel like we've thought about that a lot since then, and I'm personally not convinced that random variables are a good model for this type of error. And so I want to note this quote from Jorge More and Stefan Wild. Sorry, Stefan couldn't be here. This is the first sentence in their abstract on estimating noise in a computer model. It says, computational noise in deterministic simulations is as ill-defined a concept as can be found in scientific computing. Okay? And I really kind of want to end this little section with that, because I think that encapsulates the issue that we're dealing with when it comes to computer simulation, which is that really we don't have a good model for computational noise such that we can analyze it. Right? Within classical numerical analysis, we'll often do something that feels like perturbation theory. Now within probabilistic numerics, they want probability density functions or probability distributions on this numerical noise. I understand the perturbation theory. It's local. It kind of makes sense in a local sense. But also I was sort of brought up in that tradition, so it feels right to me. Again, it's kind of a human thing. So let me end with some summary thoughts, and then we'll do some practical advice. Summary thoughts. Computer models are deterministic. Despite what my mom thinks, a computer model is deterministic. If I run the computer twice, it ought to give me the same answer if I give it the same inputs. I say despite what my mom thinks because my mom's often calling like, oh, my computer did something random. And I'm like, no, Mom. It's not random. It just did whatever you told it to do. You just didn't tell it to do the right thing. But so they're deterministic. And so in my opinion, approximation tools are better suited because I have one function. Right? I have one model that I care about. Some engineer came and said, I care about this particular flow model and it has these inputs and these parameters I'm interested in and this is the thing that I want to compute. That's one function. My postdoc likes to say, what happens if a function walks out of a dark alley and you want to approximate it? Right? I really like that way of thinking about it. Like, wow, some function came to me and I need to assess some properties of it before I figure out how to approximate it. So although I do believe this, also computational noise is really annoying if you take it seriously, right? So you mentioned that the data didn't have any noise in it, and so we have this sort of like interpolation property for a lot of these approximation methods. But should we be interpolating? If we only know sort of our function values to a couple of digits, like should we be interpolating? If we overfit in the sense of statistics, what is it that we're fitting? We're fitting some kind of error that we don't really have a model for. So to me, there's lots of fundamental research opportunities for applying statistical methods to noiseless data, which is this approximation setting. And so I kind of want to leave you all with this to say that, well, I've got another slide of advice after this. But I want to say this because I think that this type of conference is really an opportunity to dig into some of these fundamental research opportunities. Okay, and then I tried to be Bayes frequentist agnostic, which really betrays the fact that I'm not a statistician. So for my interview, I was at School of Mines for 4 years in the Applied Math and Stats department. My interview with the most senior statistician, I sat down and I said, you know, Bayes frequentist, like what's the big deal? Yeah. So I still got the job, but I'm also not there anymore. So. So that's interesting. But I know a lot of people from the computer experiments world that are like, well, if you take a Bayesian perspective, then everything makes sense. I'll agree that everything is consistent, but I'm not sure everything makes sense. Okay, so here's some advice. We'll go back to this. Civilized conversation and argumentation. Okay? Now, making caricatures is fun. We can laugh at it. It's a good way to connect with people because, again, part of this is just talking to other people, right? But don't be mean. Just don't be mean. That's all. Statisticians, I would encourage you to include numerical experiments that demonstrate asymptotic convergence of your testing error or your generalization error. Right? This is often not done, or it's done very half-heartedly in a lot of the statistics literature and computer experiments. Why? Because they're not brought up to think about asymptotics in the way that we think about asymptotics related to the error. Numerical analysts. Convergence analysis of statistical standard error and bootstrap standard error in the context of constructive approximation. Right? So remember, we said that with regression, they have these error estimates that they can compute. What the heck do those mean in the context of approximation? I don't know the answer to that, but I think it's a really interesting question. And I think that as we move more towards applying machine learning to data derived from computer experiments, we really ought to try to answer this question. Right? Can we use bootstrap to actually get some relationship to the error in the sense of approximation? And then lastly, as practical advice, somebody needs to write some review papers on these for some cross-disciplinary perspectives. Okay, that's my time. We're at the point of questions. If you have questions, now you can ask them. If you don't, I have a couple questions up there that are pretty generic that you're welcome to ask me. Otherwise, I'm Paul Constantine from the University of Colorado at Boulder, and thank you very much for your time.